Okay, ready for this. We're taking a deep dive into something pretty big today. The Schrödinger equation.
Oh, that's a good one.
Yeah, it might sound a little intimidating at first, like something you'd only hear in a physics lecture hall.
Right.
But stick with us because this deep dive, I think we're going to make it surprisingly accessible. Fun, even.
Fun. Okay, I like it.
Yeah. And we've got a ton of cool stuff to pull from articles, papers, all that good stuff to really break this down.
Awesome.
And our mission here, I think it's to understand how this equation, this one equation, basically changed how we see reality, like down at the smallest level.
It's really fascinating, right? Because the Schrödinger equation, it's not just some, I don't know, abstract math formula. It's like a keyhole.
Oh, a keyhole. I like that.
Yeah, a keyhole that lets you peek into a totally different way of seeing the universe, like down at the tiniest level.
Right, like we're going down the rabbit hole.
Mhm.
But instead of white rabbits, we've got electrons doing all sorts of crazy things. Like sometimes they're particles and then poof, they're waves.
Yeah, that's the wild part of quantum mechanics, isn't it? Wave-particle duality.
Mm-hmm.
It's one of those ideas that just boggles the mind.
It really does.
But, I mean, it's what the Schrödinger equation is all about. Like, it's not telling us exactly where a particle is.
Oh, okay.
Instead, it's giving us the odds, the probability of finding it in a certain state.
So hold on, let me see if I'm getting this. It's not like a GPS tracker for electrons.
Right.
It's more like what? Like a weather forecast saying, hey, there's a chance you'll find an electron over here.
You got it. That's a really good way to put it. It's a completely different way of looking at reality. Like, in our big world, things have definite spots. They're solid. They're predictable.
Right, right.
But in the quantum world, it's all about maybes,
Mm.
possibilities.
Mm.
It's fuzzy.
Fuzzy. Okay, so that brings us to like that Heisenberg uncertainty principle thing, right?
Yeah.
Where you can't know both where a particle is and where it's going at the same time.
Absolutely. The more you nail down one, the fuzzier the other gets. Like, nature's putting a limit on what we can know.
Huh.
And the Schrödinger equation, that's the tool that helps us work with that fuzziness.
So it rolls with the punches, so to speak. Instead of being like, the electron is right here, it's more like, well, here's a map of the likely spots.
Yeah, exactly. Like a heat map, showing the hot zones where we're most likely to find it. And that map, that's what we call the wave function.
Okay.
And it's represented by the Greek letters psi a. It's a little intimidating, maybe. But don't let that scare you.
Yeah, Greek letters, always going to have the Greek letters.
Right. But it's basically just a fancy equation, one that holds all the info we can possibly squeeze out about a particle.
It's like the particle's resume, listing all its skills and where it might be working.
Uh-huh. I like that.
So something I was thinking about when we were getting ready for this deep dive was the whole time-dependent versus time-independent equations thing. What's the difference there?
So think of it this way. The time-dependent equation, it's like watching a movie, seeing how things change, how they evolve. But then there's the time-independent equation. And that's more like a snapshot, a frozen moment.
Okay.
It describes systems where the energy stays the same, like electrons in those nice stable orbits around an atom.
Oh, okay. So it's like a still life of the quantum world.
Yes, a very good way to put it.
So we've got the Schrödinger equation itself, then the wave function, and then these different types of equations. But how do scientists actually, solve these equations? I mean, to figure out stuff about a particle.
That's where the real fun starts.
Yeah.
But honestly, it can get a little tricky. I mean, the equation itself, it might look kind of simple, especially if you know calculus.
Right.
But trying to solve it exactly, except for like a few very specific situations, that's really hard.
Oh, wow.
Even with all the computer power we have these days, we often have to use, clever approximations, shortcuts.
So it's like a really, really tough Sudoku puzzle.
Yeah.
Where you need some extra tricks to crack it.
Exactly. A perfect analogy.
Sure.
But when we do solve it, it's a big deal. We get super precise info about how matter acts down at the atomic level.
Wow.
Take the hydrogen atom, for example. It's one of those special cases where the equation can be solved exactly.
And that solution, it predicts those specific frequencies of light that hydrogen absorbs and emits, right? Those spectral lines that are like a fingerprint for each element.
Exactly. It was a huge win for quantum mechanics because it showed the equation wasn't just some math theory. It had real-world power, predictive power.
Yeah.
And that's just the beginning.
Oh, man, I can't wait to dig into more of this. So what else can this equation do? Can it handle things that are more, more complex, like multiple particles or things moving super fast?
That is a fantastic question. And it takes us to some even more mind-boggling parts of the quantum world. We'll have to get into relativistic quantum mechanics for that one.
Okay, sounds like we're about to go warp speed here. Listeners, buckle up. We're just getting started.
I'm ready.
All right, welcome back, deep divers. So before we jumped to warp speed, we were talking about how the Schrödinger equation works great for simple systems like that hydrogen atom. But what about when things get more, I don't know, more intense, like particles moving so fast they make a rocket look like it's standing still?
Yeah, then we got to bring in the big guns.
Right.
Remember how we said the basic Schrödinger equation doesn't deal with relativity?
Right.
It's like using a street map to navigate, interstellar space. You need a whole different kind of map for those speeds.
Do we need what, like a quantum GPS for these particles on a cosmic road trip?
Exactly. That's where the relativistic versions of the Schrödinger equation come in. They take all that mind-bending stuff from relativity, time dilation, length contraction. All that becomes super important when you're dealing with particles at, relativistic speeds.
Okay, my brain's already starting to hurt. What are these souped-up quantum equations called?
Well, two of the most famous ones are the Klein-Gordon equation and the Dirac equation. These are like the heavy lifters of quantum mechanics, built for those super-fast particles.
So I guess if the Schrödinger equation is a nice car for getting around town, these are like, what, our supersonic jets? Ready to break the sound barrier.
Yeah, perfect analogy. The Klein-Gordon equation, actually, historically, it came first, even before Schrödinger's. But it worked for particles that don't spin.
Yeah.
Imagine like tiny billiard balls zipping around super fast. That's Klein-Gordon territory.
Okay, so that's for spinless particles. But what about particles that do spin, like our electron friend? Where does the Dirac equation come in?
The Dirac equation, that's a masterpiece.
Yeah.
It not only brings in relativity, but also that intrinsic angular momentum of particles, what we call spin. And you know what? This equation, it actually predicted antimatter.
Whoa, antimatter. So that's like what? Particles that are like the evil twins of regular matter?
Exactly. The Dirac equation, it basically said, hey, for every particle, like an electron, there's an antiparticle. In this case, it's a positron, same mass, but opposite charge. It was a revolutionary prediction. And guess what? They actually found it later.
Wow, an equation predicting something that fundamental about the universe. That's wild. Our sources, especially that Wikipedia article on the Schrödinger equation, they go into some of the nitty-gritty of these relativistic equations, but I think the takeaway is they're more complex, but way more accurate for these super speedy particles.
Right, and they've changed how we understand particle physics, like the fabric of the universe itself. They explain things like particle decay, how those particle-antiparticle pairs get created and destroyed, even how particles act around super strong gravity, like black holes.
So we're not talking about just little electrons and atoms anymore. This is like the fundamental stuff of reality and how it acts in these crazy cosmic environments. Now, there's another thing in that Wikipedia article that caught my eye. Fox space. Sounds kind of Star Trek-y, doesn't it?
It does. A little bit, yeah. But Fox space, it's a big deal in quantum field theory. It's like this math framework that helps us describe systems where the number of particles can change.
Wait, hold on. A changing number of particles? So particles can just like appear and disappear? Poof!
In a way, yeah. In quantum field theory, particles can be created and destroyed. It's kind of like a cosmic game of musical chairs, but the number of chairs keeps changing.
Okay, that's a wild image. So how does this Fox space help us understand that whole particle creation and annihilation thing?
Imagine you're trying to describe a system in regular quantum mechanics. You'd use a wave function for each particle, right?
Mm-hmm.
But in Fox space, you're describing the whole system. And it could have 0 particles, 1 particle, 2 particles, a whole bunch. It's like having a wave function for every possible combination of particles.
So instead of one wave function, we've got this giant set of them, each for a different particle setup.
Exactly. It's how we deal with the fact that in the quantum world, the number of particles isn't always set. They can pop in and out, and Fox space handles that beautifully. And here's the amazing part. The Schrödinger equation. It can be extended to work on these Fox space wave functions. Gives us a way to describe systems where the number of particles changes.
Whoa, my head is spinning. It feels like with this Fox space and these relativistic equations, we've gone way beyond that simple electron in an atom. Like we've entered a whole other level of quantum weirdness.
We have. It's a peek into quantum field theory, where particles are excitations of these underlying fields. And space-time itself, it's not just a background, it's part of the dance.
Well, listeners, we've gone from the basics of the Schrödinger equation to these mind-bending relativistic versions, and even touched on this crazy Fox space thing. But there's one more stop in our quantum journey. All right, welcome back, explorers. It's been quite a ride through the quantum world so far, right?
It has.
We've been digging into the Schrödinger equation, from the basics to some really mind-bending stuff. But every invention, every big idea, it has a story behind it.
Yeah.
So I think it's time for a little history lesson. Let's go back in time and see how this revolutionary equation came to be.
I like it. Little time travel.
Yeah.
It's a journey that takes us through some of the biggest moments in physics, like moments where our whole understanding of the universe just shifted.
Okay, dramatic. I like it.
And, we really got to start with Max Planck. He had this revolutionary idea. Quantized energy.
Okay, quantized
He
energy.
was trying to figure out something that had physicists scratching their heads for ages. The spectrum of black body radiation.
Black body radiation, okay. Sounds kind of spooky. What's that?
Well, it's the kind of radiation, that the electromagnetic radiation given off by something that just absorbs all radiation, no matter the frequency or angle. Imagine a perfectly black object. It sucks up all the light that hits it, then re-emits that energy as radiation. The problem was, classical physics, it couldn't explain what they were seeing.
So like Newton's laws, Maxwell's equations, all that, it wasn't working.
Exactly. The predictions didn't match what they were measuring. And that's where Planck comes in. He said, what if energy, instead of being continuous, is actually emitted and absorbed in little chunks? Quanta.
Quanta, okay.
It was a radical idea, really shook things up.
Like saying, instead of buying apples individually, you can only buy them in bags of 5.
Perfect analogy. It was totally different from the way people thought about energy back then.
Yeah.
They thought it could be any value. Planck's idea. It was met with some raised eyebrows, let's just say. But it turned out to be the key to solving that black body radiation mystery. And it set the stage for, well, I think you know who's coming next.
Oh yeah, the big one. Einstein.
Exactly. Einstein.
The rock star of physics.
He took Planck's idea and ran with it, applied it to light itself. He said light's not just a wave, it's also made up of these little packets of energy. Photons, we call them now. And that, my friend, was the birth of wave-particle duality.
So light, something we always thought of as a wave, can also be a particle. It's like saying water can be both a liquid and ice at the same time.
Really messed with people's heads, right?
Yeah.
Because it challenged everything they thought they knew about, well, reality.
Yeah.
But the experiments, they backed Einstein up. And that led to another big step forward. In 1924, Louis de Broglie, a French physicist, he comes along with this really bold idea.
Let me guess. It has something to do with those matter waves we talked about earlier.
You got it. De Broglie, he was thinking about that wave-particle duality with light, right? And he's like, wait a minute. If light, which we thought was a wave, can also act like a particle, then why not the other way around? Why can't particles act like waves?
So instead of asking why waves act like particles, he's asking why particles act like waves. Mind blown.
It was a brilliant insight. Really paved the way for our main man, Schrödinger.
Schrödinger, finally. I was wondering when he was going to show up. He must have been pretty excited about this whole matter wave idea.
Oh, he was all over it. Schrödinger, he was fascinated by these matter waves, and he wanted to find the math, the equations, to describe how they worked. He was thinking about the connection between optics and mechanics. You know how, in some cases, the way light travels, it kind of looks like the path of a particle in classical mechanics.
So he saw this link between how light behaves and how particles behave. He's thinking, there's got to be some deeper connection here.
Exactly. And that's what led him to, well, drum roll please, the Schrödinger Equation, 1925.
A big year.
A huge year for physics. This equation, it was a game changer. It gave us the mathematical tools to understand how matter can be wave-like.
It's crazy how one equation can revolutionize our understanding of, well, everything. The Wikipedia article, it mentions that Schrödinger actually tried to make a relativistic version first. You know, one that took Einstein's relativity into account. But he hit a few snags.
Yeah, the results he was getting, they didn't match up with what experiments were showing at the time. So he said, okay, let's focus on the non-relativistic version for now. Turned out to be a good move.
Sometimes you got to take a step back to take 2 steps forward.
Right. His non-relativistic equation, it nailed those spectral lines of the hydrogen atom. That was a big win for quantum mechanics, showed that his theory was on the right track.
It's amazing how this one equation has had such a huge impact. I mean, think about it. Lasers, transistors, computers, even quantum computing, it all comes back to this.
It does. It shows you the power of this equation. It's not just some abstract math thing. It's a tool that has unlocked a deeper understanding of the universe. And that understanding, it's what's led to all these amazing technologies that we use every day.
It's mind-blowing, right? That something this fundamental came from a scientist basically wondering, Why do light and matter act so weird?
It really shows you the power of curiosity, of scientific thinking. And the journey's not over yet. Scientists are still studying the Schrödinger equation, figuring out all its implications, pushing the boundaries of quantum mechanics. Who knows what other mysteries this equation might unlock in the future?
Well, listeners, that brings us to the end of our deep dive into the Schrödinger equation. We've covered a lot of ground, from the basic ideas to some really complex stuff. Its history, its impact, and it's really amazing, isn't it?
It really is.
The world of quantum mechanics is full of surprises, and this equation, it's one of the keys to understanding it all.
So keep exploring, keep asking questions, and keep wondering about the universe and all its mysteries.
And until next time, keep diving deep.